Okay, today we're going to talk about program proofs with an introduction to loop invariants. So I'll start by starting with a really simple program. Okay, we got you take the average of two numbers. Great, we make an assignment. Make an assignment here. We add a second number to our temporary variable. We return that variable's value divided by 2. Depending on if this is an integer divide or a regular divide, I guess, this will return you the average of, let's say, two floats. If their floats come in, okay? Obviously, this is a really simple program. The proof is not interesting, not any more interesting than the program is, okay? We're going to start with it anyway. Great, after the first assignment, we've made an assignment. After another assignment, we've made an assignment. And then we return our variable, okay? So great, the proof looks exactly like the program. And somehow if we even make the program a little bit longer, like, oh, what if we take the average of 3 things? Our proof isn't any more interesting. We decide we're going to take the proof of 6 things. Now our program's really ugly and the proof isn't any more interesting than before. It's still quite boring. The reason they're so simple is because this method, I mean, we don't call any procedures. We call plus, we call divide. We don't call any other methods at all. Specifically, we don't have any recursive calls. We don't have any loops in our program. We don't even have any conditionals, okay? So now if we wanted to add conditionals into this, we could say, great, well, now we're going to take the max of 2 numbers. Great, assign one of them, assign a temporary variable to one of them. This is, of course, not really how you'd write this program, but and then check if the other one's bigger. Great, make a different assignment and return it. This is a bad way to write a simple function. But the reason I've written it this way is because then the proof sort of, you know, there's enough room to write a proof at least. It's hard to write a proof for a one-line program. In this case, the proof, again, looks just like the program. We have this conditional within the program. Well, the proof also has a conditional. If something happens to be true, then do one thing. Otherwise, don't do that thing. And some assignment that was made before continues to be exactly the same. So anyway, we've got this conditional. Great. Still not so interesting. Let's go back to our average, but now we're going to stick in a loop. So great. Now we're going to take the average of 3 things, but instead of 3 separate variables, we're going to imagine that we have an array of 3 values. We set temp to 0. We go through this loop. After we go through it one time, well, I equals 1, we assign one value, then I gets changed to be 2, gets incremented to be 2, then we add our second value, then I gets incremented to be 3, we add our third value, and then we return something, right? We could also change our notation around here a little bit. To use something a little bit more like the book's notation, I could subscript all my variables, right? So I can say, I sub 1 is the value in variable 1 the first time, in variable I the first time through the loop. I sub 1 is 1, temp sub 1 is A of I, or A of 1. Then, rather than sort of crossing out my old values, I just have new assignments where I sub 2 is the value in variable 2 the second time the loop. So on. We go through this, right? And then again, we return after we finish. We finish, great. Okay. So notice, this is still, basically we're just unwinding our entire algorithm here. I mean, we could imagine stepping through the algorithm step by step. Well, first I is 1, we increment temp. I goes to 2, we increment temp. I goes to 3, we increment temp. We step back up here again. I might be incremented to 4 in some sense. Well, that's not in the range from 1 to 3. And so we exit the loop. I maybe disappears, and now we return whatever's in temp variable divided by 3. Okay? So even though we have a loop here, our proof that it just unwinds that loop and pretends the loop isn't really there, right? You could use that even if the loop is longer. You could use it if the loop is up to 10. It'd get a bit redundant after a while, but you could. You could use it if the loop went up to 1,000. It'd be a pretty boring YouTube video, I suppose. You could use it if the loop went up to 10 million, but then YouTube probably won't even take the video. So anyway, regardless, nothing fundamental changes about that proof until we start talking about a variable sized loop. Even if you have a loop of 10 million, you could imagine unwinding this program into 20 million separate steps and 20 million separate assignments and seeing, and even if I haven't actually written them out, you could ask me, oh, what's the 5 millionth step? And, oh, the 5 millionth step might be I equals 2.5 million, something like that. Right? On the other hand, that proof sort of exists even if we haven't written it down. If we try to expand that exact same proof into this system where we have a variable sized array, I can't tell you how many lines there are in my proof, right? I can't say, well, I have a 20 million line proof. I mean, how many lines are in this proof? 2n. Wait, n is a variable. If you give me a fixed proof, it shouldn't have a variable number of lines to it, okay? So in this case, we could try to take the same approach, right? We could say, great, start out, I got I of 1, we got temp of 1, we got I of 2, temp 2, I 3, temp 3. And the question is, when do we get to stop, right? At some point in time, we want to stop. The way that we're going to do that is we're going to come back at these and look at, well, what's happening to temp? I mean, this loop, the purpose of this loop is to change the value in temp and change it in a very specific way. And in general, I'm going to say every time we finish this line, just after this line executes, every time temp equals the summation j equals 1 to I of aj. That's going to be true every time we get there. That's going to be called our loop invariant, okay? That loop invariant is going to hold whenever we get to that spot, okay? We've already seen that this holds for I equals 1. This is the first time we got there. The first time we got here, well, temps of 1, we saw equals a of 1. Well, if I plug in 1 for I, because I equals 1, if I plug in 1 for I have the summation j equals 1 to 1 of a of j. Well, that's just a of 1. So this loop invariant holds the very first time we complete this line. That's called the loop invariant initialization. The next thing we're going to want is called maintenance. Given that the loop invariant holds on a given on some iteration, prove that it holds on the next iteration. Maybe I shouldn't have used I here. It doesn't have to be I from the variable. But given that it holds on an iteration, prove that it also holds on the next. Okay. And then finally, the thing we're going to look at is called termination. That's when do we leave the loop? What conditions hold that force us to leave the loop? And after that, we should be able to figure out what it is that the loop accomplished. Okay? So let's see. In this case, we have this loop invariant. We want to say, great, our initialization is, well, temp temps of 1 equals, we already saw, it's the summation from 1 to 1 of aj, which is a of 1. Well, that held, that's fine. Okay, now we want to say if the statement happens to hold the last time through, imagine I equals n. Okay, that's going to be our last time through the loop when I equals n. Well, if this statement holds temp equals the summation from j equals 1 up to n aj, great. That's going to sign temp for us, okay? That's going to be our last temp assignment, and then we're going to return that summation divided by n. That will tell us what the loop does, and in this case, what the loop does pretty easily tells us what the program does, okay? We'll come back to that. The middle step is sort of the most complex part. It is, it's like, look, if this statement holds for the ith iteration, prove it holds for the I plus first. Or if it holds for an arbitrary iteration, prove that it holds for the next iteration. That's going to be a proof by induction. Okay? So let's see. In this case, we're given that the loop invariant holds for some iteration, and we want to prove that it holds for the next iteration. Okay, we want to prove it holds for the next iteration. So, temp prime I'm going to use as a variable to represent temp one iteration later. I prime also I one iteration. A prime will also be A one iteration later. And what we're going to do is we're going to look at the program itself to figure out how do temp I and A prime change. Now, well, this is the line that changes I prime is equal to I one iteration later, which is just I incremented by 1 from how we interpret this for loop. Temp prime is equal to the old temp value plus the next A prime I prime. That's by observation of the program. And A never changes. So A prime equals A everywhere. A never changes, okay, in this program. So now, once we have that, we have our given. We know how all the variables change, and we're trying to prove something. If we know how all the variables change, we don't actually need the code anymore, all right? So now I've got my given, I've got the thing I'm trying to prove. All this is right from the previous page, and these are how the variables change within each iteration, okay? So what I'm going to do is I'm going to say, great. I know that A prime I prime is equal to A prime I plus 1, which is equal to A of I prime plus 1. By these two, we know how variables change. And I want to know, does this equal, do we have temp prime equals, right, this is this term over here. So let's see. I want to know, these two terms are the same. Okay? Do we have temp prime equal this thing over here? Well, I can simplify this by noting, well, I prime is equal to I plus 1, A prime is equal to A. Now I want to know if this is true, okay? By induction, I know what temp is. I have this nice statement about what temp is, okay? I know what temp is. And I can plug that in. I can plug that in for this temp, okay? So that's what I'm going to do. When I plug in for that temp, great. Now I have, I've plugged in for the temp with this summation. Well, now I have a summation from j equals 1 to I plus the I plus first term of the same form. That just equals the sum from j equals 1 up to I plus 1, which is exactly what I'm trying to prove. So temp prime equals this. That's what I'm trying to prove. Great. So I know, now I know, because this thing was true on the first iteration, by my maintenance property, it must be true on the next iteration. And if it's true on the next iteration, it must be true on the iteration after that. Basically, my maintenance proves if it's true for an arbitrary iteration, it has to be true for every iteration after that, okay? And then finally I say, okay, great. What does that invariant imply when the loop ends? Now in this case, what happens when the loop ends? I equals n. We go through this thing the last time. Temp sub n equals temp sub n equals j equals 1 up to n a sub j. And great. We end up having temp is equal to the sum from 1 up to n of a sub j. Probably to be complete, I should have something else in my loop invariant. it looks so silly that I didn't want to put it. Anyway, I sub I equals I. Ith time through the loop, variable I gets value I. And that's actually how we'd be able to plug into our top I value. Say, oh, when I equals n, well, I equals n at the end, I sub n equals n. Anyway, I ignored that because it looks so ridiculous to put, but I guess maybe I should have put it anyway. If I want, let's see, if I want, instead of evaluating my loop invariant right after this line, I could evaluate right before that line, okay? And if I evaluate right before that line, so now I'm evaluating here. If I evaluate before that line, my loop invariant is going to change a little bit, right? I mean, because now temp is equal to the summation, not including the ith term, right? Well, in that case, you might have, let's think about what happens when we get to the end of the loop. We get to the end of the loop, somewhere near the end of the loop, you're going to have I equals n. Right then, when I equals n, this loop iteration should hold. Temp should equal the sum from I equal to n minus 1 of aj. After that, temp gets incremented. You could imagine I then gets, so I should say temp gets a sub n added to it. Then I gets incremented up to n plus 1. Right then and there, the loop invariant should hold again. I equals n plus 1. Temp equals the sum from j equals 1 up to n plus 1 minus 1 is n, a of j. Sum of the first n terms of a. I don't know why I chose to start this array from 1 instead of 0, but there you go. Maybe the book does that. Anyway, so the loop invariant holds when I equals n plus 1. Then, because I is not in the range to n, we jump down to the end of the program and we return the same thing we returned before. A sub 1 summed to a sub n, all divided by n. Right? Okay. So our invariant is going to be a Boolean statement which is always true for this program. And hopefully it's going to tell you what it is that the loop does. I mean, you know, Boolean statement like 3 is less than 9 might be true, but it doesn't really tell you what any program does, right? I mean, want to be a statement which is always true for the program and which tells us what the program does. In this case, this loop is intrinsically tied to this invariant, okay? Oftentimes, our Boolean statement will be an equation, okay? But it doesn't have to be. I mean, an equation is a type of Boolean. Is it true that the variable temp is equal to this summation? That's a Boolean statement. I sort of mentioned, well, we could evaluate it in more than one spot. You could evaluate, you know, right at the start of the loop, right at the end of the loop. And if it was a longer loop, you could also evaluate in the middle of the loop. That probably is the ugliest option. You have to sort of go some steps into the loop for your initialization, and then finish up the steps of the loop after the last time through the loop to get to your termination. That's okay, you can do that. Finally, sometimes you won't even want to, well, which iteration? That shouldn't say it. Which, you should say, what iteration do you want to use for the initialization? So maybe you have some crazy loop invariant that doesn't happen to be true the first couple times through the loops. And then you'd have to sort of step through the loop for a few times until the initialization holds. This is all related to a more complex base case for the induction that the loop invariant is built on. All right. Next up, we're going to do a conversion. Go back to our conversion to binary algorithm, and we're going to prove that it actually works. Thanks.